Good morning, everyone. I'm Bill Branan, the Hodgson Director of the Digital Research and Curation Center and the Open Source Programs Office at Johns Hopkins University. I'm delighted to welcome you to the closing keynote session of Love Data Week 2024 at Johns Hopkins. Love Data Week is an international event where institutions, organizations, scholars, students, and other data enthusiasts come together to celebrate data in all its forms. This is the fourth year of the Johns Hopkins Libraries presenting Love Data Week at JHU. The celebration has grown from a few workshops to 5 full days of keynotes, talks, panel discussions, and workshops for all disciplines and all experience levels from beginner to advanced, and with speakers from within Johns Hopkins and beyond. We have been honored to welcome our speakers and their diverse perspectives. Throughout the week, we have learned how to make our research reproducible, engaged in open discourse on what makes open science and open data truly open, discovered what it means to measure democracy, and have been humbled by our responsibility to the communities and individuals we study. We would like to thank all our speakers, panelists, moderators, and workshop instructors from inside and outside Johns Hopkins who have joined us this week to share their time, expertise, and perspectives. We would like to acknowledge and thank our sponsors, the Institute for Data Intensive Engineering and Science, the SNF Angora Institute, the Alexander Grass Humanities Institute. We would also like to thank the Johns Hopkins Libraries Love Data Week Organizing Committee, who have worked tirelessly to bring you this amazing event, and the communications and marketing team at Johns Hopkins Libraries, who have promoted this week so widely. Before we begin, I would like to remind everyone to please enter any questions you have for our presenter into the Q&A box. You can use the chat to communicate with the hosts if you are experiencing a technical issue with the webinar. It is now my great pleasure to introduce our closing keynote speaker for Love Data Week 2024, Dr. Alex Szalay. Dr. Alexander Szalay is a Bloomberg Distinguished Professor at Johns Hopkins University with a joint appointment in the Department of Physics and Astronomy and Computer Science. Alex also serves as the Director of the Institute for Data Intensive Engineering and Science. Alex is an international leader in astronomy, cosmology, the science of big data, and data-intensive computing. Alex is a tireless advocate for open data and open science and has led the development of new paradigms of data-intensive science across disciplines as diverse as astrophysics, turbulence, and genomics. A recipient of numerous honors and awards, Alex received the Alexander Van Humboldt Award in Physical Sciences, the Microsoft Jim Gray Award, and the IEEE Sidney Fernbach Award for his work on data-intensive computing. Alex is a corresponding member of the Hungarian Academy of Sciences and a fellow of the American Academy of Arts and Sciences. Most recently, Alex was elected to the National Academy of Sciences and selected as a 2023 fellow by the Association for Computing Machinery in his contributions to systems, big data, open data, and for service to the community. Dr. Szalay's topic today is Science in the Era of AI. Please join me in welcoming Dr. Alexander Szalay.
Hi, thank you very much for the invitation, and it is lovely to see how data is becoming more and more central everywhere. So today I would like to talk about how science is being changed by data, especially in the era of AI, when AI is becoming dominant. So can we display my first slide? Yeah, so I will talk about science in the era of AI. And the next slide, please. So what we are right now facing a new revolution in science, which is transforming everything. And this revolution is enabled by the exponential growth in our computing. Basically, the sensors that we use to acquire new data are based on the same technology as our fastest computers, the same silicon lithography. And essentially, Moore's law is at the core of driving science. But the way it is manifesting itself, just as today's cell phones are as powerful as the crazy supercomputers of only 15 or 20 years ago. Essentially, the millions of cell phones, each of them contain also a variety of sensors, and so enabling a massively parallel scale out. And a similar phenomenon is happening in the Google Cloud or in the Amazon Cloud, where they are not building supercomputers, but they are basically hosting millions of relatively simple servers, which are not very different from the ones that sit in our computer rooms. What we see today is that there is a new paradigm of science appearing in front of our eyes, essentially reflecting the ongoing revolution in science. Can we get the next slide, please? And we can jump through this. So next, yeah. And next slide. So what we see is the exponential change of science. So thousands of years ago, we were basically collecting empirical data. So this manifested itself in the Chinese star charts, or Leonardo was drawing beautiful pictures in his codices about turbulence. And so we were essentially describing natural phenomena and capturing this in written forms. There was a change happening when Tycho Brahe gave a large corpus of his data to Johannes Kepler. And Kepler took all this data describing the motion of the planets and encapsulated these in a couple of laws. These are called Kepler's laws today, which explain the orbital relations and the shapes of the orbits of the planets, and eventually led to actually discover the laws of gravity. And this was the change into the theoretical branch, where we were being able to create new analytical abstractions, mathematical abstractions, which represented nature in the form of a few simple equations. And we were able to solve those equations analytically, making predictions about data and generalizations. And this culminated probably in Einstein's general relativity. Some of these are no longer very simple equations, they were quite complicated. And this happened only in the beginnings of the 20th century. The next turning point was when we started to use computers to solve some of these equations, which may have been simple to write down, but they were impossible to solve analytically, like the Navier-Stokes equations of turbulence. And this was first tried by Fermi and Ulam at Los Alamos. And this led to the emergence of the computational branch of sciences, which were simulating complex phenomena. And over the last few years, we have seen the emergence of data-driven science, and now we are starting to see AI-driven science, which is synthesizing theory, experiment, and computation with statistics. But basically, computing permeates every level, every phase of science. And this is also starting to require a new way of thinking. But when you look at this slide, the first phase of science, the empirical phase, lasted thousands of years. The second phase lasted hundreds of years. Then it took us a few decades to kind of go through the computational branches of science. And now we are yet in another revolutionary stage. And this is why we call this the fourth paradigm of science. And this kind of all emerged during the 10 or 15 years that I had the privilege to work with Jim Gray of Microsoft, the person who invented modern databases and transaction processing. And he spent actually many years with working our team at Hopkins on the Sloan Digital Sky Survey. And in this process, we realized this coming revolution and tried to point it out for the rest of the community. Next slide, please. So basically, this is the current change in the structure of science is different from anything we have seen before. So science started out, you can see it on the upper right, as a single discipline, natural philosophy in Oxford, in the modern European science. And then eventually it branched into physical sciences, life sciences, and earth sciences, which then started to subdivide into theoretical, experimental, computational subdivisions. But there was actually very little to overlap between, for example, computational genomics, computational life sciences, and, for example, computational physics. But today we start to see a convergence. So instead of splitting even yet smaller subdisciplines, what we see is that there is this whole area of data science and artificial intelligence, where the methodologies are very, very similar, independent of the underlying science discipline. So from medicine, earth science, chemistry, astronomy, physics, biology, all of these are kind of now attached to the and overlap with data science and AI. And in many ways, the approaches are common. Just as much as in the old sciences, there was actually one common principle. This was mathematics. So the mathematics was the heart, the glue that was connecting all the hard sciences, because generally we didn't have. So if we had to go to a friend of ours who was a mathematician to kind of solve our equations, we were in a disadvantaged position. So therefore, everybody in the hard sciences had to learn enough mathematics to be able to maneuver their own discipline. So data science is becoming the new math, the shared language of modern science. Next slide, please. Today, scientists are becoming increasingly multidisciplinary. So our traditional higher education is training deep but narrow people. I would call these I-shaped people. So as we train, from going from a bachelor's degree to a master's, then a PhD, we are getting deeper and deeper in our own discipline, but we are also getting narrower and narrower because we have to develop a sharpened focus. But as you are getting as old as I am, we are becoming T-shaped because we go to a lot of talks in other disciplines, and we develop a shallow but fairly broad layer on top of our deep I that we developed during our whole educational career. But today, what we see that this is not enough. And in a sense, to do anything in modern science, we need to grow another deep leg in data science and artificial intelligence. And this is actually not quite new. We can think back how genomics emerged. So Watson and Crick, it was a physicist and an ornithologist who got together and formed and created a new discipline. But this new discipline only emerged probably 30 years after when they started out, when so they got there in an ad hoc fashion. And there was a chaotic phase, and then the students became the first carrying members of the genomics community. And every discipline of science which is emerging has to go through this. But eventually scientists need to become pie-shaped, grow a deep lab in data science and AI as well. And today this is kind of new, but I expect that in 10 years, basically everybody going through hard sciences will have automatically grow this second leg that we won't even talk about this. But today we need to consciously train pie-shaped people, and we can see that how the machine learning classes and introduction to AI, etc., are now becoming as popular as the 101 physics and calculus and algebra, linear algebra, and they will also become as indispensable for doing science. Next slide. The granularity of science is also changing today due to these trends. Next slide. So we saw in the middle of the 20th century the emergence of big science. So when we switched from the manual production of scientific data to the Industrial Revolution, so in the 1920 to 1950, which was in many ways how modern hard sciences emerged, this was dominated by small experiments by a few individuals, growing kind of slowly, one experiment very quickly superseding the other. But after the national laboratories were created, again starting with Los Alamos, but soon followed by CERN, and then the US built Brookhaven, Stanford Linear Accelerator Center, mostly in high energy physics first. These were big science projects costing billions of dollars, and they took decades to build a new experiments, building very large tunnels underground for the accelerators. They were typically managed in a very risk-adverse fashion, because if you invest many billions of dollars, you are not allowed to fail, and involved many thousands of people. And this is a very big difference also as far as data is concerned. So in the past, as experiments were rapidly followed by one another, the data sets had a relatively short life. So much of the data that was an experiment was superseded, then the data was cited though, but everybody was citing the newest data. But today, when the big science experiments take 10, 20 years to build and another 10, 20 years to execute, they may not be surpassed by another experiments in our life, similar experiments in our lifetime. And when we look at the emergence or the evolution of high energy physics facilities, so in the 1910s, 1910s, 1920s, people built the first Van de Graaff generators. Then Cockcroft and Walton built this cyclotron in Cambridge. Then there were synchrotrons, which were already building size. And then afterwards, then came the national laboratories where the accelerators were actually kilometers long accelerator tubes. And then it turned out the United States tried to build a superconducting super collider in Waco, Texas, and then or Waxahachie, Texas. And it had to be canceled because it turned out to be too expensive for a single country. And the whole world had to get together basically to build the CERN LHC experiments, the Large Hadron Collider. But what is important, when it takes 20 to 40 years to generate a big data set, the data is here to stay for decades. The lifetime of these data sets are going to be much, much longer, and they represent a huge investment in science. Can we, next slide, please? But today, because of this, there is a problem. So the bimodal funding of the federally funded science is, on one side, there are the little $300,000 individual grants, and on the other side, there are the $10 billion experiments like CERN. There is very little in the middle. But the problem is that these $300,000 experiments are in some sense too small to actually create a breakthrough experiment. It's an exception. It's a miracle if it is possible, somebody can do that. And the $10 billion experiments, by the time they are completed, the technology is outdated. Think about the Hubble had essentially the same chips as the first IBM PC. And so the technology, they are typically 20 years, in some cases 20 years behind the bleeding edge. And so today, the optimum science is changing today. There was this vacuum in the middle, and there is much more happening there. And even the NSF and the NIH are realizing this. But typically, also private foundations are stepping in, and they donate 10, 20 million-ish grants to science, but they require a much higher level of agility. That we have to create, the people who are awarded these grants, they have to create a unique instrument in a very short time, in a few years, and therefore they can stay out at the bleeding edge of technology, use the latest computer chips, they can use the latest software, they can take risks, because it's not that much money, and they are pushing the budgets to the limit, maximize the science, and they can generate petabytes of data because they are using very advanced technology. So they are going beyond the Industrial Revolution. They are going to basically to the highly automated robotic experiments. And there is an enormous fresh creative energy liberated in this process. So this became the sweet spot of science over the last few years. And one of the take-home messages here is, even in this world, even smaller groups can generate petabytes of open data using their most advanced technologies and AI. Next slide, please. So this brings up that in this world, when the Googles and OpenAIs and Microsofts and Facebooks are investing many billions of dollars in computing and research, how can universities compete in this process? And so this is kind of an interplay between agility and tenacity. And the industry became extremely agile, even too much so. And we can certainly cannot compete with the industry in agility. But because faculty hires are for 40 years, and at a university campus, very few things can happen faster than a semester timescale. But we can compete in tenacity and high-value data. When it takes still, using this mid-scale project, it will still take 2, 3, 4 years to actually create a high-value data set. And this is too long for the Googles and Microsofts. They want something yesterday. And they can do this, of course, if they can sample it from the World Wide Web, they can get such data sets, but they are not going to build accelerators or telescopes or new kinds of microscopes. So as there are more and more mid-scale projects emerging at universities, these are generating petabytes. And much of how we use AI will optimize how we carry out the experiments and also how we discover the new patterns. But this all requires also the data sets to be AI ready, to be easy to interface to all these packages and all these AI frameworks. But when we look back on the recent explosion in evolution in AI, most of the breakthroughs came from a unique data sets like ImageNet and AlexNet. But also there are the parallels in science, that Human Genome Project and the Sloan Digital Sky Survey, for example. So they were all combined with stayed out at the technological edge. They created a unique data set using the most up-to-date sensors, but they were also all combined with a disruptive idea. But this is now where the cutting edge, bleeding edge of science is. Next slide, please. And so I was personally got into this area through the Sloan Digital Sky Survey, where Johns Hopkins joined in 1992. This kind of emerged in parallel with this genomics, so we sometimes called it the Cosmic Genome Project. And it's not a miracle, because we were using the same kind of sensors, the large format CCD chips that are now present in every cell phone. And they are also, they enable the high throughput genomic sequencing present in the Illumina sequencers. The whole idea was similar to the Genome Project, that the data that we were collecting about the whole sky by building a special purpose telescope is entirely public, open, and free. And the database was built at the AHU and has been served from here ever since the early 2000s. And today we are at Sloan 5, but the data is still coming out through Hopkins. And we typically had so far about more than 10 million distinct IP addresses using the database. Jim Gray had an integral role in working with our team here at Johns Hopkins to build this and create this database, which really became an experiment early on how could you actually create a new kind of data access, an interactive access that can reach into, at that point it was terabytes, but today into petabytes. And what is remarkable about this, that how fast it was picked up by the community and how widely it was used, as there are only 15,000 astronomers and our 10 million distinct users indicate that there are internet scientists, quote unquote internet scientists, who are using the data. And they actually made a lot of really remarkable discoveries. They discovered new kinds of galaxies that made some of the pictures kind of collected or discovered by these groups have made into the cover of Science and the cover of Nature. So in this process, scientists are becoming publishers and curators of large data sets, because the models that used to work in the past, that we were handing off our data to the publishers, are not working any longer, simply due to the sheer scale of the data. Next slide. So we learned a lot of lessons during this process. For example, statistical analysis work much easier with the databases than flat files, because it enforces referential integrity. Collaborative features are essential. We also had to go beyond SQL scripting. So SQL was wonderful while we were still doing aggregates and filtering, but when we started to use machine learning on top of it, we had to integrate with Jupyter and various deep learning toolkits. Everything is spatial. We needed to build very good spatial indices, not just for Google Maps and navigating in our cities, but also navigating on the sky, or navigating in tissues, or navigating turbulent flows. when we created data sets, there was no single access patterns. There were multiple different access patterns, from the high-level visualizations, interactive explorations, and then batch analysis of petabytes. In order to create data sets which are clean and have statistical reproducibility, we need automation to generate. We need to eliminate humans from the loop, because it also slows it down and it introduces an additional source of error. And doing the scaling out was much harder than we ever thought. And we always had to preserve the deep links to the raw files in order to also verify that the new discovery we just made was not an instrumental artifact. And probably the most important word of all of this is how to earn the trust of the community. What are all the things that you have to do so that people trust that you will actually release the data? The data is a consistent and high quality. There are no hidden bombs in there. And in many ways, it is very hard to build. It always takes years to build up the trust, and it can take just a week to lose the trust if something bad happens. And one of the other lessons was moving petabytes of data is hard. And you have to be actually smart about it. You can't just do brute force. So the key lesson that we learned in all these is that we had to find the right trade-offs. We shouldn't try to do everything for everybody. Next slide. How does data analysis evolve? We have seen how the music industry has completely transformed the music publishing. So I used to be able to go to a Virgin store and buy an LP or a CD of Miles Davis. And then I took it home and played it on my own record player or CD player. And iTunes has substantially changed this model. I no longer had to buy a physical copy of anything. And especially I didn't have to buy a whole LP if I didn't want to. I could buy the songs one song at a time. I bought a digital copy, I still own that, and I downloaded this digital copy to my personal device and played it through my MP3 player. But what is emerging today is yet another major step, that everything is happening somewhere remotely in the cloud, and I'm getting as a feed of the music. I don't own the music anymore. I can specify in a broad sense my likes and dislikes. And this is coming to my device, but I have no idea at this point also what is the underlying format of the music, how it is streamed, whether it's MP3, MP4, or whatever. All it's happening as an auto negotiation between my device and the cloud provider. What are the data equivalents? We used to take an experiment or exchange data. We were sending tapes and disks, or even in some cases a computer with the data. So this is the LP and CD equivalent, that essentially we had to download the data or take the data to our own device. What is the iTunes equivalent? This is the SQL databases that we have been building, that there are these large data repositories, and I can write a SQL query and I can download a chunk of data, basically one song at a time. And it still comes down to my device, and I played it with the data locally on my own servers. But what is emerging is kind of Google Colab, and where we are heading with the Szalay server here at Hopkins, is that everything happening server side, so they're near the data, and we basically just get a feed. We see a stream of the results in our own personal device. And in many ways, we don't even care whether the data is in a database, or is it in flat files, or is it a mixture? What is the file system? Is it an NFS on the server, or is it Windows, or is it an S3 object store? We don't care. We care about just getting a stream of the relevant results. But this also means that our scientific software needs to be kind of analysis ready and cloud optimized if we wanted to plug into these processes that happen in the clouds. And this was pointed out recently by Ryan Abernethy, who is an oceanographer at Columbia. Next slide. Aggregating data. So next slide. Implications of big data are multiple. It has multiple implications. First of all, what are the errors in big data? Typically, in any data set, there are two kinds of errors. Statistical, which is tied to how many independent data points do we have. And then there are systematic errors, which are the instrumental biases occurring during the data collection process. The statistical errors decrease with the size of the data set as the square root of n, where n is the number of data points. Collecting big data needs parallelism and scale out. So generally, the big data is coming from using many similar inexpensive devices. Many of the remote sensing data is like places like Planet Labs is coming from the use of microsats. So lots of cheap satellites, or we have the digital watches, each of them having accelerometers, measuring the blood pressure, or even recently measuring the oxygen level and so on. And so basically, this is happening, and the same thing is happening in the computational cloud when there are millions of relatively cheap computers connected and operating in parallel. Okay, but these similar sensors, in order to be cheap, they are not going to be identical. They will be similar, but because of the cost savings in the manufacturing process, there will be basically every one of these sensors will be actually different. And so this means that all these systematic errors are introduced by these subtle instrumental biases. And if it's in your face, then we call it calibration and do it. But there is for every error that we calibrate out, there are probably 100 other errors which are too small to calibrate and remain undetected until it actually impacts the science that we try to do. So in most of the scale-out projects, the biggest challenges are these systematic errors, but this can be corrected in software. However, these are particularly important for AI training sets. If the data is too noisy and too contaminated by systematic errors, basically it's garbage. We get garbage out. And this has been plaguing some of the early AI projects where this really impacted the outcome in an adverse way. So this is an area where I think AI is going to actually bring a lot of potential improvements. So what if the AI can actually learn and discover these systematic errors? So that we create a special neural networks which are going after these systematic errors in our data sets. Next slide, please. There are also statistical and computational challenges with the scale out. So basically, if everything is driven by Moore's law, the data volume and computing power each roughly double every year. Actually, it's every 18 months. But this means that no polynomial algorithm can survive only n log n, because imagine that, for example, one of the basic statistical principles are the minimal variance estimators. That if we have a covariance matrix, the inverse covariance, we have to weight the data with the inverse covariance matrix. This is if we have n data points, then the matrix inversion is roughly n cubed. So imagine that I have a data set consisting of n points. I can do this analysis today on my computers. Next year, my data is growing to 2n. The speed of my computers is growing to also to 2n. But the task, if it scales as n cubed, it will become 8 times more expensive. So basically, my computations will become 4 times slower, even if I upgrade to the latest computers. So the problem today, so this is why basically we have to switch algorithms. And we need to discover the systematic errors, but we also need incremental algorithms where computing is becoming the part of the cost function. So many of these optimal algorithms from the past are built under the notion that they are optimal to extract the signal from a noisy data if we have exactly, if the primary source and the primary loss is due to the small number of points. But it's implicitly assumed that the cost of computation is 0, that n is so small that this is much easier to do the statistical computation than to collect the data. But this turns around when we have billions of points. So out of billions of points, we need computational methods that how can we get where time is critical, what is the best result we can get out in a minute, in a day, in a week, or in a year. It is very similar to like training a neural network. The longer we train it, the more accurate the results become. But sometimes we don't need, in all the cases, it's more important to have a result fast enough than actually crunching it to the maximum accuracy. Next slide. So the main challenge in creating big data sets is very often data aggregation. And it's very difficult to aggregate data sets where the joint analysis requires bringing all the data to the same location. And the most frequent mistake is when people try to create these aggregated data sets, which are not quite identical. They are creating the mother of all databases. They are trying to build integrated ontologies, so common dictionaries and data models where they integrate the two data sets. But this is becoming polynomially complex. Imagine we are bringing in a third data set. Then we have to integrate this with both 1 and 2. And if we bring in the fourth data set, it needs to be integrated with all the previous ones. And so this ontologies and this integration process is becoming increasingly complex. And it is also becoming less well-defined. And our philosophy is essentially keeping it simple. So we bring in a lot of different data contexts, which are each of the inside of each themselves. They are very well documented and self-contained. And we basically enable the users to create their own cross matches and links between those, because there is very often not a single way to do a mapping between two data sets. There may be sometimes multiple paths, and you take the identifiers in both of those data sets and create your own identifier and use this for the science projects. But such a way we can just drop in all these new data sets independent from each other and give the tools to the users to create these references, these links, and then we track those. And the most frequently used links are basically brought into the public domain. So we are uniquely capable of managing many petabytes of data, how we can actually support these aggregations with a linear complexity. Next slide. The other thing that over the almost 30 years that we have been working on these large data sets, we saw a lot of repeating patterns for data-intensive projects, and these are remarkably similar actually to each other, deep down in the trenches. And so now what we are trying to do is to take these processes and turning these patterns and turning them into processes that we can replicate in a conscious way instead of discovering this by trial and error. And what we noticed that this requires actually a couple of critical roles in a sustainable human infrastructure. We need to have a kind of what we call architects, implementers, disruptors, trainers. Architects are the people who build the bridges between the projects and the people who are going to implement the kind of back office for the systems. Then the implementers are the ones who actually create both the prototypes and the production version of the code. Then once we build the whole data system, there come people who are the disruptors who then suddenly have an idea and they use the system in a very different way how it was originally actually designed for. And then everybody realizes that this is actually the right way of doing these types of analysis. And then we need trainers who actually teach the broader science community how to use these facilities and the data sets and the new features. And we are trying to create here at IDEAS a sustainable model for massive data and compute infrastructure. We have to figure out the right balance between what do we do on the premises locally and what can we do in the cloud. and what is more efficient to do in the cloud, and how can we help people best in providing an active support in creating these new data resources. So it turns out that it is really hard to build sustainable funds for preserving high value data. I would like to talk next. So all of these require ongoing commitments, and these are not just one-shot investments, basically buying just a set of computers and dropping them into a computer room. Next slide. So the mid-scale science can lead to game-changing data, and here are just a small palette of a bunch of projects done at Hopkins, following the Sloan Sky Survey, where we try to build these subsequent projects faster and faster, learning essentially from the mistakes made in one and carrying the experience into the next one. And these range now from astronomy to the turbulence database, where we delivered hundreds of trillions of points to the world, which provides an immersive sensors that you can drop into supercomputer simulations. We are building Astropass, where we are trying to increase the data intake by a factor of 1,000. And in the Poseidon project, we are building a virtual observatory for 2.5 petabyte ocean circulation model, the highest resolution model for ocean circulation ever. So basically, we were able to create unique leapfrog projects, which were non-incremental steps in their respective science areas. Next slide. And this is just a picture of the turbulence database. So at this point, the latest was, I think, a few weeks ago, that we are at this point at 300 trillion points that we delivered to the world. Next. And this is the project with Janice Taub, that we tried in cancer immunotherapy, where the holy grail is to figure out how the immune system is interacting with cancer cells, and why these cancer drugs work. And currently, they only help about 20% of the patients. And how can one actually discover which patient is going to respond to which drug? Basically would dramatically cut the cost of treatments. So this is what we have been working on. And it turns out it's remarkably similar actually to the Sky Survey. We are taking multicolor image pyramids. We segment this into cells and split them into tumor cells and immune cells, very similar than taking multicolor images of the sky, segmenting them and splitting them into stars and galaxies, depending on the shapes. And to date, we have now about roughly 600 million detected cells, but we had to go through 22 trillion pixels, and the whole Sloan Sky Survey was about 7 trillion pixels. So this is actually commensurate effort to the biggest sky surveys. Next slide. The AI, in this world, the AI is emerging. Next slide. So much of what we do in science today in AI is related to the posterior analysis of the existing data. And it's about recognizing patterns, compressing the data, finding anomalies. And the recent developments with large language models is amazing, so that how they can actually recite much of the literature as a response to an English question. At the same time, we have to be beware, of the famous hallucinations of ChatGPT. Next slide. And so how can we intelligently use the LLMs in science? One area is where we have so far completely failed, is to solve the long tail problem. So I think at this point, we know what to do with the terabyte and petabyte scale data sets, because these are important enough that we focus and spend enough energy to preserve them. But for every one of these data sets, there are 1 million small files sitting somewhere on lab computers, etc., generated by digital instruments, which are small, and some of them appear as tables in papers, but most of them are just sitting on the hard disk. And essentially, whenever we try to capture this, it was a total failure. But a lot of these show up, for example, as appendices in papers or posts in web pages. We could use actually LLMs to harvest data in a lazy fashion and then figure out the context of the information about the data from the surrounding text in the paper. And in science, we actually can do quite well because we have typically the list of co-authors. So all this corpus of papers by a set of people who collaborated for a decade have a fairly concise dictionary. And we can extract all these dictionaries automatically. And so an AI framework, we could build an AI framework which can extract not just the data and put it into a searchable form, but also what they mean and what is the broader context. Next slide. We could also use LLMs for automatic code generation. Okay, so I don't know how many of you have used Jupyter, but when you explore data in a Jupyter notebook, you start out with a clean sequential set of cells, and then you try a whole bunch of things, and by the end of the day, it's kind of all a jumble. And many of the cells have been executed out of order and so on. And wouldn't it be nice if there was just a button on a Jupyter notebook that I could press and then have Copilot basically rewrite my code? I could say that this cell was my starting point, and this is the cell that it gave me the result that I wanted, and show me the shortest path between those two cells, and throw away all the blind alleys that I have tried in before. Next slide. We don't like black boxes. We need to know what is happening inside these black boxes. And physics of AI is one of the fastest emerging sub-area of AI, how it is trying to figure out what is going on inside the neural network. Why do they learn? And how do the initially random weights of a network evolve and develop long-range correlations? It's like a phase transition of a physical system, but they can find actually symmetries of a physical problem, for example, that it was demonstrated recently in turbulence or in other areas. Next slide. And furthermore, today finding the systematic errors, this is becoming the biggest problem in collecting large data sets. And this has been a black art. And couldn't we actually feed all our instrumental parameters to a neural network and train it to find all these correlations between the instrument parameters and the output data sets, which can be actually quite small, but the data set is large. And we can, so there is a famous example about turbulence, about tuberculosis, where the classifier that identified tuberculosis was actually the age of the X-ray machine, because all the samples which contained TB positive patients came from basically outside the United States, from much old 20, 30-year-old X-ray machines. So the removal of systematics, finding the optimal calibrations could be entirely automated instead of relying on black art. And this is, so the expectation is the AI will be probably just as important as our data acquisitions as it is in the analysis. Next slide. If I ask you, do you have enough data or would you like to have more? I don't think there is anyone in science who would say, I don't want more data. But when you think about it, this is actually, this was an ill-posed question because I didn't specify that what kind of data would you like to have more? And many of our challenges are finding needles in a haystack. Okay, and sorting through just an ever bigger haystack is actually not what we want. What we want is to all together collect smaller haystacks which contain more needles. We need to, so on one extreme, if we capture everything, we store everything, we spend all our money on disk drives. If we collect too little data, then we may throw out actually the needles, we throw out as the baby with the water. So the LHC, the high energy physicists, did a very intelligent experiment. They spent 10 years while the LHC was built they spent 10 years in creating Monte Carlo simulations that captured all of the known physics and they predicted all the known events coming from the accelerators. And then they created filters on the detectors themselves, where they throw away all the events that correspond to known physics, and they only keep 1 out of 10 million events, and that is still 10 to 100 petabytes a year. So we will have to adopt this behavior, and this is how actually AI can, next slide, how AI can help us. We need to collect more relevant data. So basically, if we are finding needles in the haystack, but we don't know what the needles look like, we actually know very well what the hay looks like. So we could build basically neural nets that generative models which can essentially recognize which events, incoming data points are consistent with the known corpus of science. And we don't have to throw it all away like the particle physicists do. We can just subsample. We can keep 1 out of 1,000 of those so that we still have a representative sample, but we can increasingly focus on the tail onto the unknown. And we are trying to do an experiment with the help of the Schmidt Foundation. How can we put a target selection in a large telescope into a reinforcement learning loop? So how can we find the most important targets and learn from our errors if we targeted the wrong objects? So capturing in one elevator pitch soundbite, if an AI algorithm can drive our cars, why cannot it run our microscopes and telescopes? Next slide. Can we skip through this? So basically, many of the challenges we are facing with open data is not technical. But we have to realize that the value of our national investments, the billions of dollars we spend on science every year, is in the digital data that it produces. And these high-value open data sets will be relevant for decades, and it will result in much more data reuse. But it's not enough just to throw this data on a hard disk and leave it there. There is also much of this data are today being presented by smart digital services, and there is also a service lifecycle. The data is becoming smarter, and the smart platforms need to be maintained for decades. Next slide, please. So basically, the $100 billion plus that he invested in experiments, that it's leading to today's open science data. It's a national treasure. It must be preserved. However, the federal funding cycles are short-term, and they are also the review panels, etc., are primarily aimed in spending much of the money in creating new science. And so therefore, essentially, there is no coherent policy how to preserve these very high-value data sets. When you think about, we created the Smithsonian more than 100 years ago to host a physical specimen from historical scientific discoveries, and it emerged as a public-private partnership. Where is the Smithsonian of data? If we don't create it sooner or later, there will be a high-value data set which will be lost. There will be a major embarrassment, there will be a congressional investigation, and then 5 years later, somebody will do something. But could we actually do this without losing high-value data? Next slide. So summarizing, the challenges are non-technical. We have seen there are 4 paradigms of science, how we went from empirical to theoretical, computational, data-driven, and maybe now the AI is actually will turn out to be the 5th paradigm. The organization of science is changing, and the granularity of science went from small to bimodal, now to mid-scale. And basically, we have data sharing and long-lived data. We need to accelerate this change, and it is happening quite naturally. The mid-scale data is happening over a few-year time scale. We see a changing relationship between scientists and data. Previously, data was only in papers, now in big data sets, and we are undertaking curation responsibility. But in this world, we still need a trusted data intermediary, which empowers sharing and reuse of data. The future is automation is the key. because there is so much data generated, we cannot keep up with this data and curating this data by hand. This has to be done by AI tools. And the curation of this high-value data sets is crucial for the future. AI is changing science, and we only see the outlines of this future because it's changing so fast. Every aspect of science will be changed by AI, how we do our experiments, how we collect our data, how we actually analyze our data, and even how we actually curate our data. Lots of challenges are ahead, how to compete at a university, who to compete with. But this will completely transform universities, the way we teach, the way we actually create science, and the way we actually preserve science, and how we train students. And this picture kind of represents the ocean of data, and the sun is just rising. So this is not sunset, but it is sunrise, looking ahead, to this brave new world that we are just about entering. Thank you very much.
Thank you, Dr. Szalay, for an insightful and thought-provoking talk. I think we have time for maybe just one question that came up during your discussion, and that is with small-scale data sets, it's easy to pinpoint and fix errors in the data. How do you do that with large and mid-scale data? Can it be hard to catch those errors since it's really difficult to examine the raw data at that scale?
Yeah, well, I think this is an area where AI could be incredibly useful and applicable. The other is that also put out the data to the public and allow people so open up the data and basically listen to the people who are using it. So I think on what we saw on the Sloan, that there were basically lots and lots of reports, and people found a lot of small errors in our data, and we responded. The challenge is also how to manage version control in that case. So you can't. So how do you avoid the error of that you fix an error, but that this is already done a different version of the data? So what we ended up doing is we did once a year data releases. And in the meantime, we created a list of the known errors, but they were all propagated to the new version. And then we published a paper in the regular literature related to the new data release so that people could coherently cite, even this was actually before, the various links to data sets where actually the DOIs became available. So we built a bridge to the traditional citation mechanisms.
Perfect. So there were lots of other questions. I'm afraid, unfortunately, we're out of time, though. So I'll ask everyone to please join me in thanking Dr. Szalay for this wonderful talk. And although today is the last day of Love Data Week, we have 2 more events that are upcoming. Next, from 11 to noon, will be a series of session talks around the theme of analyzing the archive, working with data from text, audio, and video. And then this afternoon, join us for a workshop on using the open science platform SciServer that Dr. Szalay spoke about, that was developed and supported by the Institute for Data Intensive Engineering and Science. Thank you all, and enjoy the rest of Love Data Week.
Yeah, thank you very much.